Aside from the matter making up cosmic objects like planets, solar systems, this galaxy, what could constitute 93% of the total matter and energy in our whole universe? That's where dark matter and energy come in.
These are various portions of our universe, as observed by the Hubble telescope. All of them, like the whole universe, are dazzling and fascinating. They're filled with all kinds of cosmic wonders, from planets to galaxies, and scientists have had to solve our universe, like a puzzle. To scientists, the universe is a puzzle, a spectacular, infinite, and challenging game that they have been playing for centuries. And we have found many parts. But there is a major piece of the universe that we have several clues about, but have yet to fully solve.
But first, we need to see some of the pieces we have found so far. Various scientists have found the puzzle pieces to show that our solar system is in the heliocentric model with the sun, not the Earth, at the center. They found that planets travel in ellipses, not perfect circles, around the center of their solar system. By the discovered laws of gravity, as the distance between two cosmic objects increases or the sizes of the two objects decrease, the gravitational attraction between them decreases. Also, scientists have proposed multiple theories explaining how the universe began, most notably the Big Bang and steady-state theories. And in another great theory, among others, scientists have proposed that space-time is connected in one dimension and is essentially the fabric of the universe. Gravity is the distortion of an object in space-time, and cosmic objects travel in a straight line around other objects in that distortion. Through great questions, answers, and endeavors from scientists like Stephen Hawking and Albert Einstein, we've solved and found many pieces, but we can see that there are some missing, which leads us to the question to find them. What is the universe made of? The cosmic objects you see in this picture, and this picture carry much more matter and energy than is held in just the stars and galaxies, the visible stuff. Most of it is not composed of particles of ordinary matter that makes up many things we're familiar with, like water, grass, the moon, clouds, our Earth, and the sun. It's labeled dark matter and energy and makes up about 95% of the total matter and energy in our universe. Dark matter doesn't absorb, reflect, or emit light, so it makes it rather hard to detect. But we do know it exists because of its gravitational effect on galaxies. Stars in some galaxies move and spin around each other at such fast velocities that require the gravitational pull of much more matter than is seen in the combined mass of their stars and dust. The more mass, the stronger the gravitational pull, and faster the speed. This is what Fritz Zwicky found in the Coma cluster. By measuring the total mass of galaxies by looking at their rotation curves, it was found that there were speeds of 2 million miles per hour for 50 times their mass accounted in the galaxies of the Coma cluster. So, he assumed that there was an unseen type of matter. Sinclair Smith found the same for the Virgo cluster. So, scientists have come to the theory that dark matter essentially holds galaxies spinning around each other. Additionally, pictures from the CMB show that from disturbances or little ripples in the fabric of the universe, only 5% of the matter and energy is normal matter, 23% is dark matter, and the other 72% is what we label dark energy. The CMB, or the cosmic background radiation that was present or is present from the Big Bang, uses radiation that matches with frequencies of different types of matter and energy. Another piece of evidence comes from investigating the formation of light elements in the soup of the Big Bang in a process called nucleosynthesis. The soup of protons and neutrons in the early universe combined to make heavy hydrogen, helium, and lithium nuclei. It's revealed that during this process, there are parameters on how much normal matter can exist. And from that, we have reaffirmed that only 5% of the total matter and energy can be in the form of normal matter. A crucial method to finding out more about dark matter is gravitational lensing. Previously mentioned was the theory that gravity is the distortion of an object in the fabric of space, and this is known as the theory of general relativity. This theory also shows that mass in space bends light when it comes close to an object due to its large gravitational field, and the light will refocus somewhere else. If an object has a lot of mass, the bending of light around that object will be rather large. Dark matter is found where normal matter is, like galaxies. If a person on Earth was looking through a telescope at a faraway galaxy, they can sometimes see two images through their telescope because there is perhaps a cluster of galaxies with a lot of dark matter in the middle. The light from the distant galaxy will bend around that cluster, and the person on Earth will view its position as different from where it is in reality. So, if a galaxy has a lot of dark matter, with the addition of some normal matter, light from distant galaxies will be distorted by its large gravitational field, by its mass, and will cause a circular or doubled image in their telescope. So, it's clear that lensing is crucial to finding where dark matter is because the amount of lensing, or distortion of light, is directly proportional to the amount and distribution of dark matter. The more mass, the more dark matter, the more gravitational pull, the more light bending. There is also dark energy, which is nothing like the energy we're familiar with on Earth, the energy that is defined by how much work an object can do. Previously mentioned was the fact that the universe is expanding, and this was discovered by Edwin Hubble. This expansion is not slowing down. Scientists thought that this expansion was slowing down by the force of gravity, which attracts objects to each other. Instead, the expansion is speeding up. Scientists theorize that dark energy, dubbed repulsive gravity, is counterbalancing the force of gravity and is leading to the faster expansion of the universe. It's like a battle between the attractive force of gravity and the repulsive force of dark energy. Right now, dark energy is winning. For example, in reality, if you jump off the ground, you'll eventually come back down because gravity is pulling you back down onto Earth. However, with dark energy overpowering gravity, if you jump, you'll keep going up and up and up, faster and faster and faster into the atmosphere. That's pretty much all we definitely know about dark energy. Everything else consists of theories. If dark energy is Einstein's mysterious cosmological constant that he referred to once, or if it is, hopefully not, a mistake of Einstein's theory of general relativity. Our universe is an enormous, infinite puzzle that scientists are still trying to solve. We're still unscrambling and fitting the pieces of what our universe is made of. But soon, through great questions and work, we will hopefully solve the puzzle.